Okay, hello and welcome to another video on applied electronics. So I'm going to continue with solving the quiz questions. So if you look at, we've already solved applied electronics RP162-A. That was for the first group. Then the second group, that's what I'm going to solve. So that will be RP162 group B. Now, so let's get started. So let's start with the first question. Briefly explain ionic and covalent bonding. So when you talk about ionic bonding, that is the transfer of electrons from one atom to another, right? And then when we talk about covalent bonding, we have a situation where electrons are being shared between atoms. For ionic bonding, example, you can think about sodium chloride, right? You have, for example, sodium is having, we know that it's having one valence electron, and then chloride is having 7 valence electrons. So as a result of this, when you combine these together, the sodium will donate an electron to the chlorine, so that both of them will have complete outer shell. Now, when it comes to covalent bonding, example, we can think about water, right? So we have, again, this time we have oxygen, but oxygen is having 6 valence electrons. So, and then while hydrogen is having 1 valence electron. So you can see that the 1 electron, we can use 2 hydrogen atoms. So these 2 electrons will then be shared with the oxygen atom. So you end up having water, which is H2O, right? Now, moving on to the question 1B. Explain the classification of materials using the energy band diagram. Okay? Yes. So we know that when it comes to the energy band diagram, right? We have, for example, we have about 3 different bands. We have the field band, the valence band, and the conduction band, right? So when it comes to the field band, that corresponds to the inner field shells, right? And then when it comes to the valence shell, that represent the valence kind of electrons parts of the atom. Now the conduction band, that's where free electrons exist. So electrons in that band, they are able to conduct electricity, I mean they are able to move around and then conduct electricity. So in classifying different material using this type of band diagram, what that means is that when it comes to, for example, insulators, we tend to have a huge gap, right, which is an energy gap between the valence band and the conduction band, which means that a lot of energy is required to move an electron in the valence band into the conduction band, where chemical reaction and other activities can take place. Now, when it comes to semiconductors, they tend to have a little band gap between the valence band and the conduction band. So as a result of this, little energy is required to move electrons into the valence band. Now the last one, which is conductors, right? When you have conductors, the conduction band tends to overlap the valence band. So as a result, you don't really need energy to move an electrons into the valence band. So as a result, you can see that once you have a conductor, meaning you have free electrons which are there, and as a result, the conductor can easily conduct electricity. So those are with the how you can use the energy band to classify different materials into insulators, semiconductors, and then conductors. Now let's go to the next question, which is question 2a. Find the forward current and forward voltage of the silicon diode as well as the load voltage when the silicon diode is operating as a complete diode. So here we are talking about silicon diode, so that means that we know that the barrier potential of a silicon diode is going to be 0.7 volts. So this is the barrier potential. All right, so we have this as a, let me write here, the barrier potential of silicon is 0.7 volt. So if you have such a diode, and then as you can see on this diagram, figure 1, you can see that we have a voltage source of 12 volts, then a low resistance of 470 ohms. So what that means is that if this diode is being operated as a practical diode, meaning we put here practical, it means that the diode here, we can replace it by its equivalent diode model. So what that means is that the place where we have the diode, so I can replace that diode by 0.7 of its barrier potential, and then we have a closed circuit. Then we connect everything. So I have here, and then I have the source, and that is 12 volts. So we have something of this nature. Okay, so this is now a new diagram. So you can see that once we have this, here is what, 0.7 volts. So once we have this, we can apply Kirchhoff voltage law to this loop. So as you can see, Kirchhoff law to this loop. So we have 12 volts minus the voltage across the resistor, the low resistor. We know that current that is going to flow through the resistor here is going to what? The forward current, right? So that is the current that is also passing through the diode. So as a result of this, we have here, the voltage across the low resistor will just be the current which is passing through it. We know that is the forward current, then times its resistance. Then as it continues, we have the 0.7 volt from the barrier potential, so it's going to be a drop, so we have minus 0.7. right? So here is we have to use this as a question as a complete diode. So here, okay, I have to change this order. Question here says complete diode, not practical, so let me correct this. So in that case, meaning when it comes to now the diode, the equivalent diode model is now going to be, we add the dynamic resistance, and the dynamic resistance is equals to 10 volts. So here should be RD RD is equals to 10 ohms rather. So we have RD being 10 ohms. So here, that means when we come here, we have the current that will passing through the RD is going to be the forward current as well. So that means I have 10 times the forward current equals to 0. So as a result of this, we have 12 minus 0.7 over 470 plus 10. So I have 12 minus 0.7 divided by 470 plus 10. So we have 11.99. Right, 11.99. So who is just like 12? You make it 12. That is just going to be 12 amps. So we have 12 amps here. So that is for the current, and then we have to find that will be the for the forward current and the forward voltage. Forward voltage meaning that will just is the same as the voltage across the diode, and the voltage across the diode is going to be the diode component. You know, since it's being operated in as a complete diode, meaning we have the barrier potential at 0.7 plus the voltage across the dynamic resistance, which is going to be the forward current times that resistance. So we have 0.7 plus forward current, we know is going to be, okay, I think let me do the calculation for this. 107 12 minus 0.7 divided by, oh, I did this wrong, divided by 470 plus 1 plus 10 rather. Yeah, so here there is no 0 point, it's not 12. So here, let me change this. It's actually calculation here was a mistake. So this will be what, 23 rather 0.54 milliamps. So we have 23.54 milli times 10. So this times 10 plus 0.7. So we have 905.41 millivolts. So we get this, okay, as the answer for this. Now going to the next question, which is explain how NPN bipolar junction transistor works. So this is similar to what was given to the first group A, but this time you have to explain how NPN bipolar junction transistor works. So here again, when we have NPN bipolar junction transistor, it means that we're having two N regions and then one PN regions. So the two N regions are more doped than the one P region, right? So this one too, again, when it comes to the connection, the emitter base junction is connected in forward biasing, and while the collector base junction is being connected in reverse biasing. And as a result of this, the majority electrons which are in the N regions of the emitter, they try to move into the P region where you have majority holes, so that they can force their way to the positive terminal of the bias voltage of the emitter base junction, right? So the voltage which is connected to that junction. So they move into the P region because the P region is slightly doped. So they recombine with all the holes, and then you end up having excess amount of electrons. So what happens is that some of the electrons will move into the N region side of the collector terminal, and then try to move to the positive terminal of the bias voltage which is connected to the collector terminal, right? So as a result of this movement, you have the flow of current, and then what is going to happen is that we have this diagram. I will just indicate how the current will move. The current flow moves in the opposite direction. I will just indicate the current direction on the NPN bipolar junction transistor. So you can see here when it comes to NPN, meaning we have here as the N region, P region, and the N region. So here's the emitter. So when it comes to the movement electrons, we know that they are moving from the N region to the P region. So the movement of the holes is in the opposite direction of the movement of electrons. So if the electrons are moving this direction, that means the holes are moving the opposite. So when it comes to the current, now we have the emitter current moving in the opposite direction to the movement of electrons. And then again, the same to apply to the collector current is going to be moving inside. And then the last one, which is the base current, so going to move inside. So you can see here again, when we try to use Kirchhoff's current law, we get the emitter current to be equals to the base current plus the collector current. Okay. Now let's see. Let's go to the last question, which is the last question. Illustrate the symbol of each type of bipolar junction transistor. Each type of bipolar junction transistors and indicate the direction of current. So first we have to illustrate the symbol of each type of bipolar junction transistor and then indicate the direction of current. So how do you go about it? First, let's start with the symbol. We have two types of bipolar junction transistors. We have the PNP and then NPN. So let's start with NPN. So let me indicate this one too as well. So let's say we start with NPN. The symbol is just going, we use the current direction of current. You can see that the current tends to leave the emitter. So here is our emitter. The current is leaving. So that's for NPN. NPN. So the next one is PNP. That one, the current is entering. So we have the current direction is this way. So as we can see, let me make it better. Let me make it here. Okay. So meaning now we can know our, based on the indicating the current, we can know this is the emitter. Here too will be the emitter. And then here I have collector. And then here is a base collector. Now the current direction on the base. So you can see here, if the emitter's current is leaving IE, in the base current will be entering, and the collector current will be entering as well. Here is the base current is entering, the collector current entering the base, so meaning this base current IB will be leaving, this one too will be leaving. So we have this. So this is how you go about answering question 3. Okay, so we come to the end of this video. See you in the next solution. Bye bye.